The first clue appeared in a support ticket. A customer claimed they had just upgraded their subscription plan, but the system still treated them as a free user. At first that sounded like a simple caching issue, but then another message arrived, then another. Users were reporting missing transactions, outdated dashboards, and recently created accounts that did not seem to exist. Meanwhile, the production dashboards looked perfectly healthy. Error rates were normal. CPU utilization was steady. Database query latency was low. Nothing suggested a major incident, but something clearly was not right. Then someone ran a query directly against the database replica used by our reporting service. The result came back instantly, and the timestamp on the newest row was almost 3 weeks old. Our platform ran on AWS with a Kubernetes cluster hosting the application layer. Traffic averaged roughly 6,000 requests per second during business hours. The platform supported payment processing, analytics dashboards, and user management. The main transactional database was PostgreSQL running on Amazon RDS. For performance reasons, we used read replicas to offload reporting queries and analytics workloads. The primary handled writes and critical reads. Replica databases served reporting APIs and internal pipelines. Replication between the primary and replicas used asynchronous streaming replication. Application services connected through separate database endpoints depending on workload type. The Kubernetes cluster hosted around 180 pods across multiple namespaces. Services were deployed through GitHub Actions pipelines using container images stored in ECR. Monitoring relied on Prometheus and Grafana for infrastructure and Datadog for application telemetry. In theory, replication lag alerts were configured to notify us if a replica fell behind. From the user perspective, the issue was confusing. New transactions were completing successfully. Payment confirmations were sent immediately, but analytics data looked outdated. Support agents checking reports also saw stale information. The main API endpoints behaved normally. Any service using the reporting replica returned outdated results. Monitoring looked healthy. Replication processes appeared active. Network throughput was normal. CPU usage was minimal. What looked suspicious was the replication lag metric itself. It was not alerting. In fact, the metric showed only a few seconds of delay. That contradicted the actual data. The first hypothesis was application caching. Perhaps the reporting service cached old results. Engineers flushed Redis caches across the cluster. Nothing changed. Next, we suspected a query bug. Maybe the analytics service was filtering the wrong date range. We executed raw SQL queries against the replica directly. The results confirmed the issue. The newest records were nearly 20 days old. At this point, we knew replication had stopped. But the metric still reported lag of only seconds. That suggested the metric was misleading. We pulled detailed PostgreSQL replication status from the primary database. The connection existed, but the replication slot had stopped advancing weeks earlier. Meanwhile, the replica database process still believed it was connected and healthy. Slack channels filled quickly as engineers from the data platform team joined the investigation. Business teams began escalating because analytics reports were completely unreliable. Finance systems depended on those reports for daily reconciliation. The root cause turned out to be a silent replication failure caused by disk saturation. About 3 weeks earlier, the replica storage volume had reached its maximum capacity. This was due to unexpected growth in temporary query logs. PostgreSQL could not allocate space. Replication stalled at that point. However, the database process itself remained running. Because the connection remained established, our tools interpreted the replica as healthy. Lag metrics were based on confirmed write location rather than actual data freshness. The first priority was restoring accurate reporting data. We provisioned a new read replica. RDS created the new replica instance and began streaming fresh data from the primary. Once the new replica caught up, we redirected connections to the new endpoint. Total recovery time was roughly 40 minutes once the problem was identified. However, historical reporting data during the previous 3 weeks required recalculation. What actually failed was not PostgreSQL replication itself, but our monitoring assumptions. Observability should focus not only on system health, but also on correctness of the data. That incident reminded us that a system can look perfectly healthy while quietly serving the wrong answers.